1, right? Because the first time we look at it, if we had left it at 0, the first time we look at it, we'd look at array element 1, which would be the second element. Okay, great. So yeah, again, we need to account for that incremented grade. Any other questions about this code?
I'm not seeing how it's going to make what's happening to the grades, making a histogram. I don't see how that if you have the same number, is it going to go back to the cell and add it to it, or?
Sorry, I didn't.
I mean, I don't understand how this is going to work, setting up a histogram. Like when you have, let's say you have 5 grades that are the same.
Okay,
So how do you account for
let's go back through. So there was some confusion about how the histogram was built. So let's take a minute and go back to the histogram code, right? So what we're doing here in this for loop is we're iterating over every grade that was input. So at each iteration, user is inputting a new grade. Right? So we're going over the total set of grades across students. Every time we see a grade, we access the element of the histogram for that grade, and we're incrementing. So if you see the same grade multiple times, on multiple iterations of this for loop, you're gonna increment that element of the array. So that's how you end up with multiples. Okay. Great. Any other questions? Okay. So let's move on to another problem. So let's say you want to calculate all of the primes up to a number n. So we've gone over calculations for checking if a number is prime, but here we want to find and print out all of the primes between 2 and some large positive integer n. So one possible solution, building off of the examples we've seen previously, is to test every integer in the range, right? And to test if each one of these integers is prime. And so you can look at that previous code, or try to rederive what we did, and just build a giant for loop that's checking these numbers one by one. Now, this is very inefficient, and it's even inefficient if we're using some of the best ways to test prime numbers. It turns out that there is a much better solution, and it's the sieve of Irikov-Sanders, and we'll describe that solution here in detail. We need to use arrays to implement this solution. So first, let's pretend that all of the integers in the range 2 to n are prime, right? So you start off, you have that assumption. I haven't checked yet, so I'm just going to assume that it's prime. So you go through, and you see the number 2. You can confirm that 2 is prime. We know that by definition. But we know that if 2 is prime, that all of the multiples of 2 are not prime, right? All of the multiples of 2 above that cannot be prime, because you can divide any of those multiples by 2 and have no remainder. So we need to go through every multiple of 2 and mark it as something that's not prime. Okay, so we do that, and then we get to 3, right? We still need to check 3 because 3 is odd. So we know 3 is prime. And then we can go through and we can mark all multiples of 3 as not prime, right? Same idea. Any multiple of 3 can be divided by 3. So now we hit 4, right? We've already marked 4 as not prime. So we don't have to do anything. We can just skip it. We know it's not prime already. We get to 5. 5 is prime. And then we can go ahead and mark all of the multiples of 5 as not prime, right? And so to be able to do this type of marking, we need to keep track of our current hypothesis for each number. But as we consider growing numbers, once we get to that number, we've confirmed whether it's prime or not. Right? So again, when we hit 6, because we marked that it's not prime, we did that when we check 2, we can just skip it, and so on. So that's the basic idea. And so it turns out that we just need to check at most the square root of n such steps. And if we do that, all of the numbers in that range that remain unmarked must be prime, right? So if we've gone through and we've checked up to root n, square root of n, then that total list of numbers from 2 to n have been appropriately marked as prime or non-prime. And the way to see that is once we hit the square root of n, we must have considered a number that is a divisor, right? So if you take any number that's greater than the square root of n, if it's not prime, then it has to be divisible by something less than the square root of n. Okay. So let's build a little intuition about computing this here. So I'm going to show you a video. So in the video, as you saw, you're going to see a grid of numbers up to 100. And we're going to go through and sequentially consider them and do this marking operation. So we here consider 2, and 2 is prime, but we need to mark all the multiples of 2 as not prime. So we're just going ahead and marking them. 3 is prime. Then we go ahead and mark all of the multiples. Similarly for 5, you can skip 6, go to 7, mark all of its multiples, and so on. Once we get to the square root of n, then whatever is left has to be prime. Do you guys have the general intuition about how this works? Sorry? If I could get a show of hands, do you feel comfortable with what's going on here? Does anybody want me to go over this again? Couple of hands here. So let's just go through this video example again. So again, we go in sequence. We consider 2, it's prime, so we mark all of its multiples as not prime. Then the next number we hit is 3, it's prime. We mark all of its multiples. We can skip over 4, go to 5. Then mark all of its multiples as not prime, and so on, right? And we do that up to the square root of n being 120 here. And once we've gone up to that level, any remaining number that's not marked, we know is prime. Okay. So how are we going to implement this into a program? So integers are going to be represented in an array. And in that array, 1 is going to indicate that, 1 in that array is going to indicate that that corresponding number is prime. A 0 indicates that it's not prime. So we go ahead and we start our program here. We're defining a set of integers, n, I, p, square root of n, which will populate. Then we ask the user up to what number do they want to check. We define an array that is 1 larger than what they wanted to check. And we do this as a convenience. Right? So we could have had this C variable going up to n, having n elements. But because of the 0 indexing, it's a little inconvenient to think about. So by going up to n plus 1, we can have C of n represent n, right? Instead of having C of n minus 1 represent n. Okay, and so the first thing we need to do is calculate the floor of the square root. We've seen this in previous slides, so I'm not going to go over this again. But if you remember, when this while loop exits, the square root of n will have the floor, or rounding down, the square root of n. So now we know what the upper bound in our search needs to be. So what we do is we go ahead and we set up our for loop. And so our for loop is just checking from I equals 2 up to initially n plus 1. And we're going to add 1 to I as we go along. So initially, we're going to initialize all of these guys and pretend that everything is prime, right? So it's saying initially in our array, everything is prime. Right? Now we need to go into a second for loop where we check that assumption, right? And in that second for loop, remember we only need to go from 2 to square root of n, right? Because we're going to consider those numbers and their multiples. So the first thing we do is we say, okay, if sieve is true, if that value is true, it hasn't been eliminated yet. And that means it is prime, right? We haven't found another number that divides into it yet, so it is prime. Now, once we've decided that it's prime, we need to check all of its multiples. So we run this for loop that is going to go through each one of its multiples in the sieve array and set it to 0, because we know each one of its multiples cannot be prime. Right? All multiples are not prime. And then that's basically it. Right? Once we've done it there, we can print out the primes between 2 and n. And we'll need to use our for loop to loop back over all of the elements in our array. And if the array element is still marked as true, we're going to print out that. And so that's the entire program. So next time we'll do a little bit of a